Hi, it's Tony Veroven, and welcome to Talking Air Filtration with NAFA, National Air Filtration Association. This is a great topic here. It's Industrial Air Filtration Basics, Dust Collection 101. We're really excited to have this topic because this is not something we've really talked about a lot in the past. So we're excited to welcome our speakers, Chrissy, Klocker, and Asa Bowen from Donaldson here. I'm going to hand off the official duties of introduction and their bios over to our co-chair or vice chair of the Education and Training Committee for NAFA, Matt Brooks, here in a little bit. But first, just want to, if you found yourself here and you're like, why am I here? Who's putting this on? It's the National Air Filtration Association. So we are several hundred companies and distributing companies, manufacturers and distributors of air filtration and indoor quality equipment and filtration components. So this is really the place to be if you're involved. If you're an air filtration nerd, this is the place to be. And I mean that with all sorts of affection. So we're really focusing on education and expertise and best practices in air filtration. Just a couple of quick testimonials for NAFA here. I think Matt would probably reflect on a couple of these or mirror some of these things. Anyone that wants to compete in the industry needs to be part of NAFA. So check us out at nafahq.org. In about 3 weeks, we will be holding our annual conference in Coeur d'Alene, Idaho. So check us out. Go to nafahq.org and you can take a look at the program and see if that seems interesting to you. We've got some great topics. We also have a technical seminar in the spring in March, and that will be coming up in Atlanta this year. We're also always looking for smart people in air filtration. So if you would like to contribute, you'd like to speak at one of our conferences, put on a webinar, write an article, we would love to hear from you. Go to our website, go to the events, and go down to where it says open call for air filtration leadership, thought leadership here. Fill out that form, and we would love to hear from you. If you'd like to stalk us and follow us, please do. You can find us all over the place. We do have a YouTube channel. That's where this webinar will eventually be. A very active LinkedIn company page where we share all sorts of air filtration industry knowledge. So, and then also a LinkedIn group so that you can hang out with air filtration folks as well there. So with that, I'm going to introduce Matt Brooks. Matt Brooks is from Bearco. He is our vice chair of our Education and Training Committee. And Matt, why don't you go ahead and take it away?
Thanks, Tony. Thanks, everyone, for joining us. Just want to introduce our two speakers today. I'm really excited about the topic they're going to be talking about. First and foremost is Chrissy Klocker. She's an applications engineering manager with Donaldson's company, Industrial Air Filtration Business Unit, based out of Minneapolis, Minnesota. She's got more than a decade of experience helping customers with technical and application guidance specific to the dust collection industry. For the past 8 years, she's served on the conference planning committee. She's been an instructor on local exhaust and ventilation design and presented on the impact of combustible dust on dust collection equipment at the annual Michigan Industrial Ventilation Conference in East Lansing, Michigan. Ms. Klocker holds a BS in civil engineering from North Dakota State University in Fargo, North Dakota, and a master's in business communication from the University of St. Thomas in St. Paul, Minnesota. Also with her is Asa Bowen. He's an application engineer with Donaldson's Industrial Air Filtration Business Unit, also in Minneapolis, Minnesota. Asa supports international and external customers with application recommendations and technical sales supported related to dust collection technologies, filter media options, and local exhaust ventilation system design. He holds a bachelor's of science degrees in aerospace engineering from the University of Illinois in Urbana-Champaign. And I'm looking forward to both of them sharing some knowledge. So I'll pass it off to you guys.
All right. Well, thank you, Matt. And thank you, Tony, also for all of your help with our webinar today. And thank you to all of you at NAFA for allowing us to come and share what we know and our knowledge with with you today. So in case anyone isn't familiar with Donaldson Company, I'd like to start off with a very brief introduction of our company. At Donaldson, we have been solving complex filtration challenges for over 100 years. We're one of the largest providers of unique filtration technologies, and we excel at producing high quality filters and parts. Donaldson was founded in 1915 by Frank Donaldson Sr. At the time, Frank was working for Bull Tractor, and he enjoyed selling replacement engines to farmers across the US. Frank often met with farmers in the Midwest who complained about short engine life due to the dusty environment. And since Frank loves solving problems, he invented a filter to help prolong the engine's life. Bull Tractor, on the other hand, liked selling engines, and they weren't too happy with Frank's idea, and so they fired him from the company. It's a good thing because Frank turned his idea into what Donaldson is today. Our purpose at Donaldson is advancing filtration for a cleaner world. We have two main business units, engine and industrial, with more than 13,000 employees around the world. We're a publicly traded company with locations in over 40 countries, including more than 100 technical laboratories. And innovation is incredibly important to us. We maintain our position as an industry leader through significant investments in research and development. So why do people need dust collection? Well, a large factor is to help with worker satisfaction. Industrial processes and manufacturing create a lot of dust, and no one wants to work in an unsafe or dirty environment. To help with this, local exhaust ventilation, or LEV systems, are installed to help improve indoor air quality or help mitigate employee exposure to various contaminants. When designed to maintain properly, these industrial systems are a key part to facility housekeeping programs. Regulations may also dictate the requirement for a dust collection system. The EPA wants to make sure you're not exhausting contaminant outside, and OSHA wants to make sure you're managing employee safety concerns and hazards appropriately. And in some industries, the nuisance dust that's produced from manufacturing processes can be reused to create new products. So process owners will install dust collection systems to capture and contain the material they're working with and then sell it for additional profits. These are just a few of the industries and markets that we serve in the industrial side of our business. Metal and machining applications, such as welding or thermal cutting, ag and mining, woodworking facilities from local schools to industrial cabinet shops, automotive manufacturing in its various stages, food and beverage, and pharmaceutical manufacturing. So the purpose of our session today is to help you understand what goes into selecting and designing a dust collection system. We're going to start small in scope with a review of common dust characteristics. Once we understand what we're trying to filter, we'll discuss different dust collector technologies and how they too will help meet filtration expectations. And finally, we'll look at the big picture with a quick explanation of how a dust collection system works and some of the key components end users will want to consider when purchasing equipment. And with that, I'm going to turn it over to one of our application engineers, Asa Bowen.
Thanks, Chrissy. For our discussion today, we are going to focus on the filtration of industrial particulate. For most processes, this is typically referred to as either dust, fume, or mist. When we think about collecting and filtering dust, there are 8 important characteristics to consider: size, shape, and bulk density, how abrasive the material is, if the particulate is agglomerative, fibrous, or hygroscopic in nature, and the chemical composition. Each of these characteristics are important because they will impact both media and dust collection strategies. Nuisance dust generated from industrial processes is often measured in terms of micron sizes. As you can see in this graphic, a micron is incredibly small, which can make it very challenging to filter. Luckily, not all industrial dust is this small. In most cases, a wide variety of dust shapes and sizes are created during the manufacturing process. This makes it easier to collect and filter the material. As I said, dust from industrial processes comes in all sizes. As you can see on this graphic, nuisance dust will often range from 1 to 100 microns and sometimes even larger. Industrial fumes, typically generated from thermally generated processes like welding or cutting, may be much smaller and have a more narrow particle size range. The size of the dust or fume is important because it dictates how the dust will build up on the filter media. When dust concentrates on a media, it forms a layer or dust cake. Dust that is uniform in size or shape will create a much denser dust cake and needs to be handled differently than dust with a broad particle size range. The shape of the dust that is produced is dependent on the operation or application generating the dust. For example, a chop saw in a school wood shop is going to produce large, irregularly shaped chunks of woods. Compare that to a thermal spray application, which is going to produce more uniformly shaped spheres, like the one shown in this image. Similar to the size of the material, the shape of the dust will also dictate how a dust cake will form on the outside of the filter media. Irregular shapes will tend to build more porous dust cakes, while more uniform shapes will create a denser dust cake at a faster rate. I like to think of dust cake as a game of Tetris. Only in our case, we want to see how much dust we can accumulate while still moving air through. Having irregular shapes allows us to concentrate more dust on the media and still move air through the media at an acceptable pressure range. I'm sure you've all heard the saying, what weighs more, a ton of feathers or a ton of bricks? And while you know they both weigh the same, the volume of those two is dramatically different. When it comes to dust collection, understanding the bulk density of the material allows us to not only make better media choices, but also impacts the style of dust collector and the strategies used to collect and convey the material through the system. Dusts that have a low bulk density, meaning they are large in size and don't weigh much, are more challenging from a material handling aspect. Factors such as airflow direction within a dust collector or ancillary equipment need to be carefully considered to avoid maintenance headaches. Abrasive dust is fairly self-explanatory. As you can see in the image, the jagged and sometimes sharp edges could tear holes in media and other system components if not properly managed. Some examples of abrasive dust include sand, rock, granite, and shot blast. Abrasive dust is not just a challenge for filter media. If not sized appropriately, any component of a local exhaust ventilation system could be prone to degradation or premature failure. Managing velocities at an appropriate level through the hood, ducting, and dust collector is critical to the overall performance of the dust collection system. Dust particles that are fibrous in nature are typically long and skinny. In the image on this slide, you can see it's a mixture of fibrous pieces and likely micron or potentially submicron particulate. Fibrous dust can be generated from processes such as fiberglass sanding or grinding, or the manufacturing of other hard or brittle materials. Like abrasive particulate, fibrous dust also needs to be managed carefully within a dust collection system. Fibrous dust is often splintered and jagged in appearance, and it's these irregularities that cause the material to hold together or be agglomerative. Special consideration should be taken when selecting the media. An example, a wider pleat spacing is often required to effectively release the agglomerated material during pulsing. Likewise, appropriately sizing discharge devices will reduce the likelihood of material handling challenges. The chemical composition of the dust is also something to consider when selecting media and potential modifications to the dust collection equipment. When reviewing the safety data sheets or general information on the dust, it's important to understand any potentially corrosive or toxic aspects of the material, and in any scenario, dry, wet, natural, or burnt. It's also important to recognize how airstream characteristics could impact the dust. For example, if a collector is pulling warm air out of a building to a cold dust collector outside, condensation or temperature swings could alter the chemical composition of what is being collected. Now that we've reviewed different dust characteristics and why they are important to understand, we'd like to expand the discussion to incorporate different dust collection technologies. As you can see on this page, there are various options available to process owners, and in most cases, there are multiple strategies that could be used to filter the dust that's being generated. All technologies have their advantages and disadvantages, and they aren't the same for every application. Today, we're going to review the four main styles of dust collectors: baghouse collectors that primarily utilize felt media, cartridge collectors with a pleated media, compact collectors that use a fluted media, and mist collectors. Baghouse dust collectors have been around for a long time and are considered a proven technology. They are ideal for processes with higher dust loads and are more forgiving on challenging dust types. Baghouses are an economic choice for high airflow processes. They have a much lower replacement filter costs compared with cartridge filters. However, with the size of these units and quantity of felt bags, there will be higher labor costs when replacing the filters. Again, bag houses are considered more rugged or durable, so you'll often see them applied across a wider array of markets and applications. They are very common on higher dust loading applications like woodworking, mining, and grain processing, especially at grain terminals, as you can see on this slide, where raw material is offloaded from ships or trains. In general, felt media is more tolerant of chemistry and non-standard airstream conditions, which means you'll also find bag houses applied in cement or gypsum processing and within foundries. In a traditional bag house dust collector, felt bags are placed over metal cages and together produce a filter assembly. Media options range from standard polyester to specialty fabrics that are manufactured to combat challenging applications, which could involve high temperatures, oils, chemical compatibility, and others. Pleated bags are a newer technology and are shorter, one-piece filter element, making them easier to replace compared with a traditional bag and cage. Pleated filter bags often utilize media comparable to a cartridge filter element. Cartridge technology was introduced in the 1970s and has come a long way since then. These units are physically smaller than a bag house and have lower initial costs. They are ideal for low to medium dust loads and best suited for fine uniform dust types. Cartridge collectors can range in size from one filter element to over 200. This variety gives customers the option to apply a single collector for an individual process or group multiple processes together to a single larger collector. Cartridge technology is best suited for dry and fine particulate. It's most commonly found in the fabricated metals industry on processes like welding, cutting, and grinding. Pharmaceutical industries love that it can be adapted with features like bag in, bag out to minimize exposure to potential hazards. You'll also find cartridge collectors applied within various grain, mining, and plastic manufacturing processes. Traditional cartridge filter elements utilize a cellulose-based media. There are specialty media options for high temperature or chemical compatibility. However, these sometimes come with a trade-off, less media per element. Likewise, pleat spacing can be modified to accommodate fibrous or agglomerative dusts, but those elements will also have less media in them compared to a traditional cartridge filter. At the beginning of this presentation, I spoke about dust particle size. Manufacturing processes and the breakdown of dust as it travels through a dust collection system increase the amount of micron and submicron particulate collected on the filter element. When using a conventional media option, such as polyester felt or cellulose, dust particles depth load into the pores of the media. Improvements to media technologies were introduced years ago when manufacturers added a fine fiber layer to keep the dust on the outer surface of the media. This technique results in a more robust media that captures even submicron particulate on the surface. This process is known as surface loading and allows the dust to be pulsed off the media much more easily. Surface loading results in better pulse cleaning effectiveness and lower overall pressure drop across the filters. Both of these prolong filter life, leading to less frequent filter changes and greater cost savings. Compact collectors are a unique design that combines the filtration efficiency of a cartridge collector with the ability to handle challenging materials that otherwise would be supported by a bag house. These collectors utilize a fluted media, which was created by our engine business unit and adopted into configurations that would support industrial manufacturing applications. This often results in a smaller footprint when compared to a bag house technology. Compact collectors tend to serve niche markets where customers require low volume or airflow, yet very high dust loading. Plastic, fiberglass, and wood are all materials that work well with a compact collector. These materials are physically large in size with a low bulk density. Typically, as this material moves throughout a ducted system, it can break down into smaller size particulate. The images on this slide are from a plastic routing application. The top photo shows the bulk of the material produced and collected from the application. It's comprised of thin strands, about 10 inches long and almost weightless. But when the majority of this material is removed, you can see that there are smaller bits of plastic and some very tiny pieces. If filtered through either a baghouse or cartridge filter, modifications to the equipment would need to be made so that material does not get caught between the elements. Here's why fluted media is successful in these applications. As you can see in the image on the left, the flutes are stacked adjacent to each other to create an element. Dirty air, shown here with a red arrow, enters an open flute, which is sealed on the opposite end. This forces the air to pass through the media to an adjacent flute that is open on the clean side of the media. Smaller particulate may be able to enter the flute, but the bulk of the material, being too large to physically enter, forms a nest on the base of the filter. When the element is pulsed, the agglomerated material drops as a mass into the hopper. The images on the right side of this slide show the material handling challenges that fluted media is trying to overcome. If a traditional baghouse or cartridge technology is utilized, customers may have to physically remove built-up material from between elements or switch to filter elements with a wider pleat spacing. Utilizing a wrap around cartridge filters is another way some manufacturers will try to prevent material from packing into the pleats. While it may be moderately successful, in most cases, a long-term solution will require a new technology. All of the dust collection technologies that we've just discussed are considered continuous duty dust collectors, meaning that the filters are cleaned with compressed air or reverse air while the dust collector is in operation. I've also mentioned a key term, the dust cake, a few times now. So to help you better understand this concept, I'd like to explain how a dust cake works and why it's important. The image below is a high-level depiction of the cross-section of a traditional cartridge media. As you can see, there are larger fibers on the right with a fine fiber layer on the left-hand side. During normal operation, air and particulate are drawn into the dust collector toward the filter media. As shown below, our air is represented by the two arrows on the left and is moving from left to right through the media. As the air moves through to the clean side, the particulate is trapped on the surface of the filter. This buildup of dust creates what we call a dust cake. Over time, as more air is drawn into the collector, the dust cake becomes denser. This increases the efficiency of the media, but also restricts the airflow through the filter, resulting in an increase in differential pressure. When this happens, the filters are actively cleaned in place to reduce the differential pressure. In our image, the three arrows on the right represent the compressed air, which is used to pulse the dust from the surface of the filter. As you'll notice, not all of the particulate is pulsed off. Some fine particulate makes its way into the depth of the media, but more importantly, a residual layer of dust remains on the surface of the media, helping to filter incoming particulate and rebuild the dust cake. After cleaning, air will continue to flow through the filter media, trapping dust and particulate on the outside and allowing clean air to pass through. The dust cake will once again build up the differential pressure until it reaches a certain point. And then the filter cake will once again be dislodged with compressed air. This cycle of building and rebuilding the dust cake will continue until the filters reach their end of life. Finally, we have mist collectors. These are used to filter coolant or other fluids used in manufacturing processes. In most cases, the liquid can be filtered and reused, saving the process owner money on material and disposal fees. Mist collectors are typically applied on CNC machines, grinding, and cold heading processes. These units can either be mounted directly to the machine to keep the coolant within the process, or ducted to a standalone system. Mist collectors are different from other types of dust collectors in that they don't have an active cleaning mechanism. Instead, they use gravity to drain mist particulate down a P-trap and into a collection chamber. Mist collectors also use special mist filters, which typically include multiple stages of filtration. We started the discussion today talking about dust characteristics and then expanded the scope to include dust collection technologies. But dust collectors are only one piece to a local exhaust ventilation system. This is a diagram of how a source capture dust control system works. A fan captures contaminants and air with a hood and conveys the material through a series of ducts to a dust collector. As we just discussed, it is here that the contaminant is separated out, allowing clean air to pass through the filter to the fan, where it is then discharged to atmosphere or returned back into the facility. Within these systems, every component is selected in size based on the available dust characteristics, the required airflow, and various other application factors. In order to design a local exhaust system, it's important to start with the design objectives. What do you want the system to do? Depending on the expectations, a different strategy or tactic may be required. For example, if the goal is to minimize exposure to a hazard, hood placement and design are critical factors. If the goal is energy efficiency, design modifications may be used to ensure equipment is conservatively sized. Other factors that will impact the design include the hours of operation and the quantity of processes being collected with one exhaust system. These and other factors will all impact the overall design and volume of the dust collection system. Knowing the details of your operation allows process owners to make better informed decisions on the dust collection strategy. The two main objectives of a local exhaust ventilation system design are to accurately predict the airflow required to effectively capture and control contaminants at their point of generation, and the total energy required to produce those airflows. Just as many of you follow NAFA's air filtration best practice guidelines, we often refer to the Industrial Ventilation Manual as our guide for system design. The Vent Manual is written by the American Conference of Governmental Industrial Hygienists, or ACGIH, which is a nonprofit scientific organization that advances occupational and environmental health. The ACGIH guidelines are considered by most in the industry as the standard for proper ventilation design. They offer multiple courses throughout the year on system design, and anyone is able to attend. It's very challenging to discuss a dust collection system without mentioning some other key stakeholders. Regulatory agencies, such as the EPA, FDA, and OSHA, often require system design and performance expectations that can be challenging to meet if not built into an original design. And that's not all. Process owners may be required to meet other codes, such as local fire codes or FM Global. Each of these agencies may have design expectations to reduce process-related hazards. In full disclosure, they aren't always consistent with each other. For example, the EPA may recommend returning air from a manufacturing process back into the building to avoid excessive emissions to the outside atmosphere. On the other hand, OSHA or NFPA may recommend exhausting air outside of the building to avoid any additional risks related to combustible dust. Understanding the hazards related to the process will enable facility owners to make critical decisions upfront in the design phase. Complying with the design or code change can be very expensive and time-consuming to implement once the equipment is installed and in operation. I'd like to wrap up with a few concluding thoughts. First, no two dusts are the same. There are always going to be differences, and they may be caused by external factors. Consider both a sawdust in a dry environment and a sawdust in a humid environment. The dust is going to behave very differently when in an airstream. In addition to that, there are various types of dust collection technologies and media options available to handle any application. In some cases, there may be multiple options that could work, so it will depend on factors like physical footprint, performance expectations, and cost that will help differentiate one technology from another. When designing a local exhaust ventilation system, it's important to identify the purpose of the system. Keeping this in mind will help process owners make design decisions that work in favor of their performance objectives. However, pay attention to external regulatory agencies, as recommendations may either work in favor of or against system expectations. To help be proactive, we recommend researching what regulations or design considerations process owners may be required to meet early in the design stage. Most agencies have guidance available online for free. Finally, reach out for help when needed. Dust collection seems simple. Dirty air comes in and clean air exits the collector, but it's more complex than that. In order for the system to work, all components must be appropriately designed, and this can take years of experience to master. I'd like to open it up for questions.
Great. Thanks, guys. Asa, that was awesome. Let's see, we got a couple coming in right now. First and foremost, how do we determine what type of filter is best for applications such as cloths and fibers? If Chrissy or Asa, you want to take that?
Yeah. So Asa mentioned a bunch of dust characteristics in his presentation today, and all of those will go into figuring out which is the best option for you. But if you know ahead of time that you're dealing with a fibrous dust like cloth or fibers, you're going to want a cartridge or a filter element either with a wider pleat spacing or to go with more of a baghouse style that might have more of a flatter design to it, flatter filter design to it. The challenge is if you find out that you have fibrous dust like that and you already have a filter technology, sometimes switching to those different medias means you have a trade-off in terms of, you know, how much media you have in that filter element. So a wider pleat spacing often leads to less media in that element. And so what happens then is you're running at a higher filtration velocity and you can kind of end up reaching your filter life a little bit faster than you would with a normal cartridge element. So if you know you are working with that dust, please let people know ahead of time so that we can take that into consideration when selecting the right technology for your application.
Great. Awesome. Okay. A few more here. Is there any washable type media that we can reuse or we'll go with that. We'll just say that we can reuse.
Yeah, you know, we don't recommend washing elements. There are people who will do that, but for example, you've got a cartridge element and the most typical media that you have for that is cellulose, and cellulose is paper. So if you get a piece of paper wet, that piece of paper is going to be wrinkly, it's going to be kind of crumpled, and that's kind of what's going to happen to your filter element. So fabric filters like a felt or polyester, or if you even go with like a polyester cartridge media, it's going to be more tolerant of washing. And there are some manufacturers who will have methods for washing their filter elements. But one caution for you is if you are going to wash an element, understand that as you wash that element, those pores are going to start to expand and they're going to break down, and you're not going to get the same life out of that filter element as you would with a brand new one. So think of like from a brand new filter to its failure rate, that kind of rise in how much time it takes to get to that failure, that time frame is going to decrease as you wash those filter elements. You're just going to end up fatiguing those filters more and kind of reaching that end of life a lot sooner.
Sure, great. Okay, a couple of these. What's the best way, or how do you store dust collector cartridges? Do they need to be in a climate controlled environment?
Yeah, they do. You know, again, if it's a cellulose media, you want to make sure you've got that in a climate controlled environment so you're not subject to temperature swings, humidity, condensation. Felt medias might be a little bit more tolerant, but some of your felt medias are meant for higher temperature or chemistry, and those types of specialty medias are really going to be important that you keep those in a climate controlled environment so that you're not impacting the potential composition of the media to the point that it now doesn't meet your performance expectations.
Great. I had a couple questions about pre-wrap. So what does a collection system or application, when does it utilize a pre-wrap? And is it something that the end user might specify, or is it something that manufacturers would specify?
Yeah, Asa had this in his presentation when we were kind of talking about the challenges with agglomerative and fibrous dust. A pre-wrap is meant to go around a cartridge filter element. And what it's doing is it's kind of creating a very high level barrier. So those fibers and agglomerative particulate doesn't get stuck in between the pleats of the filter element. And so it's a very simple way to do that. But a lot of times what that wrap is really doing is trying to avoid or find a method to keep that dust out of it. it's a great short-term option, but really if you're looking for something long-term, that wrap is going to potentially compromise the effectiveness of the cleaning of the filter. So if it's a long-term solution you're looking at, it might be something more like switching to a different technology, like a baghouse filter, or even just a different media type at that time with a wider pleat space.
Great. Okay, let's see if we can get a couple more in here. And this is coming from someone that might have a little experience here. How is the volumetric flow rate of extraction air determined in the rate of capture of the materials to be extracted?
Yeah.
Okay.
This is a whole new webinar for another topic of how to do that. But we shared a slide on here about the industrial ventilation book. And really that kind of covers a lot of the information in terms of how you go about sizing a system. It really starts with, what is the process, and then what is the contaminant that you're trying to control. And so most dust will have a specific, what's called is a capture velocity. And it's kind of what is that velocity that's needed to pick that particle and get it into a state of moving that it can get drawn into the hood. So based on location and distance away from the hood, the style of the hood, and then also the contaminant itself, that velocity, and then given the shape of the hood, is going to kind of drive a required air volume for that system. But again, like you might have other regulatory factors that say, hey, although your dust requires X airflow, we're going to require you to have 10% more so that we have higher velocities in our ducting and we don't get dust settling out. So it's a bit of a game, and there's definitely a ton of factors that go into it. But that's kind of the starting spot is starting with, the contaminant, the hood, shape and size, and then figuring out your airflow at that point, and then what it's going to take to move that airflow to through the rest of the system.
Great. Okay, let's at least get one more here. How can we choose the right type of media according to efficiency, and how does that media thickness affect the air permeability and the overall system?
Yeah, choosing the right media, again, is going to go back to your dust characteristics. So what is the dust your material is handling? But the piece about the efficiency of the media, that's an interesting one. As we talked about, and Asa had that great slide that kind of showed the depiction of a dust cake. It's really the dust cake that does the filtering of the material of that air as it moves through the media. We like to say a dirty filter is more efficient than a clean filter, because you have that residual dust cake layer that helps fill in the pores of the media and trap all of that other finer, smaller particulate that might be able to pass through on a clean element. So once you have a media in there, whether it's a MERV 13, a MERV 14, a MERV 15 filter, once you have that dust cake on your filter element, all of those filters are in a sense going to behave the same in terms of it's the dust cake that's really doing the filtering and the efficiency of that filter element.
Great. A couple that came in towards the end here that I'm sure there's a couple people that actually asked this. So what's your recommendation, or how do you know when a filter has reached its end of life?
Yeah. You want to do this?
Yeah.
Go for it.
So we measure filter life oftentimes in differential pressure, and I touched on the pressure drop across a filter a couple times in the presentation. So measuring that difference in pressure as the dust cake builds up, the pressure difference will increase because there's more resistance to the airflow, and that dictates when you pulse. But as you pulse, each time more dust is still entrained in the media, less dust is going to be fully pulsed out. So your differential pressure is going to slightly rise over the course of a filter life cycle. So at a certain point, you get to a point where you pulse the filter and your differential pressure is still too high. And that depends a little bit on manufacturers, what exactly that set point is. Maybe you could expand a little bit on when exactly you want to replace, but it's all differential pressure based.
Yeah. Usually for like a cartridge, it could be about 4 or 6 inches of water gauge. Sometimes higher. For a traditional baghouse, you could have up to 8 or sometimes even 10 inches of differential pressure before that filter reaches its end of its filter life. Some of the contributing factors too, like Asa said, is when you have those filters are being pulsed, a lot of manufacturers will have different settings for pulsing. So you can pulse them continuously, like every 10 seconds. or you can only pulse the filters when they actually need it, when they get to that certain differential pressure range. And so if you find yourself that you're always needing to pulse your filters in order to kind of allow air to keep moving through, that's usually a sign that they're kind of nearing their end of life. So you can see some sort of trends, or I just start identifying that that differential pressure seems to be hovering around a higher number. Those are good indicators that you should start ordering some new filters.
Great. Okay, so got a question that's followed up on the wraps, and I guess they're looking for, someone's looking for a little guidance on mist collection filter, if wraps can be used there as well as fume. So is there applications where you would see a pre-wrap on a filter in those applications?
Yeah, you would see it on mist collectors. Some mist collectors have wraps, and the reason for the wrap on that is just to kind of keep a lot of those larger particulates, like swarf is a term that's often used in mist manufacturing, and it can sometimes be some of those metal pieces that just come along with the manufacturing process. It's to keep that type of material away from the primary filter element. So a lot of mist collectors, as Asa noted, are made out of specialty medias. They're not pulse cleaned. They really just drain and clean based on gravity or other mechanisms. And so what that wrap is doing is it's really just acting as a protective layer so that those larger particulates and pieces don't impact the performance of the primary filter.
Great. Had a couple asking about the difference or the trade-off between static pressure and the building up of the dust cake, referencing a couple slides that Asa had there.
Yeah.
Can you talk a little bit more on that?
Yeah. Do you want to take it?
Yeah.
Okay.
So yeah, and I think we touched on this a little bit earlier with the filter life cycle. You're going to build up static pressure to a certain point, and that's going to depend a lot on the shape and how your dust cake is built. If you have some of the pieces that are larger and more irregularly shaped, you're going to be able to build a big dust cake without accumulating a lot of differential pressure. But if you have smaller material that's more uniformly shaped, it's going to form a tight dust cake that needs to be pulsed more frequently. Generally, the manufacturer will dictate when you pulse. 4 to 6 inches is common for cartridge filter elements. That's kind of the standard, I think, in the industry for cartridge filter elements. Bag houses is a little bit less defined.
Yeah,
maybe
a little bit higher.
Yeah.
So one of the challenges with dust collectors is, again, they're just a portion of these local exhaust ventilation systems. So we had that slide that kind of showed you have from a hood all the way to the dust collector to the fan outlet. And in order to move that air from the hood all the way through the discharge of the fan, point A to point B is going to take a lot of resistance and static pressure. And so that's what we use in that terms, is that fan is really the key of what's designed. That's the design point that's going to determine how much volume and how much static pressure you need to move that air from point A to point B. Within the dust collector, that's where you have kind of a range of airflow. So if you have dirty filters, that dust collector might accumulate maybe 6 inches of differential pressure or 8 inches of differential pressure. But when you have brand new clean filters, it might only be, 1 to 3 inches of differential pressure. And so that range for your dust collection it will be based on what your dust collection manufacturer says. But that range in static pressure is something that you want to be able to make sure that you have enough airflow and capacity in your fan to make sure you're pulling the appropriate amount of air when you have dirty filters. You don't want to size the system based on clean filters, because what happens when you build up that differential pressure is that airflow and that capacity within your fan starts getting used up on the dust collector. And now you may be suffering in terms of how much air you're actually able to capture with your hood. So there's a lot that goes into it, but the that dust cake is really applied over a range of static pressures, over a range of differential pressure, and that's usually given to you by your manufacturer.
Great. That was awesome. Thank you so much for sharing all this this awesome information. Tony, I know we're conscious of time here. Thank you, Chrissy. Thank you, Ace. I really appreciate it. Tony, I'll hand it back to you.
Thank you so much, Matt. Chrissy and Asa, that's awesome here. As a total layperson, a person who as a marketing and sales guy and an association nerd, definitely even still learn something as so I'm a mile wide and an inch thin on air filtration, but I learned a lot. So this is really good stuff. So if I learned a lot, I know that our air filtration folks will love this stuff. So thank you so much for sharing your knowledge on this great content. Just a reminder that we do webinars and education, and you can find all that at NAFA HQ. You can follow us. If you like this kind of content, go to our website, and I think if you go under Contact Us, you can join our mailing list if you'd like to do that. We will share the slides and this webinar on our YouTube channel. You'll find that on our website. Everybody who's registered here, whether you attended or not, maybe you're watching this, you will get an email as with a follow-up link. The folks from Donaldson also wanted to share a little bit of a tool on evaluating such sort of systems here. So there'll be a link to that if you want to check that out. And with that, please, again, take a look at us if you want to follow us for more air filtration education. And keep an eye on your email for a follow-up from us. Thanks so much, Asa and Chrissy and Matt.
Great. Thank you.
Thank you.
Take care, everybody.